So good morning and welcome to our 24th meeting of Classical Mechanics 1 at CMI. Um, we have, today is 16th of December, Thursday, 2021. So last time we were discussing special relativity and in particular the concept of Lorentz transformation. So I intend to continue that discussion now. Are there any questions before we get started?
Yes, sir. I had a question about the space-time diagram for when B is in motion relative to A. I think I was confused about this last time also. I was thinking about it more.
Okay.
I can frame what my confusion is a little better now. I think so when we draw the diagram, we're doing it with respect to A, and we have drawn the path of light in a certain way in time and space. My question is, why is the path of light going to be this with respect to B?
Yeah, because light travels at the speed, same speed, no matter which observer is concerned with it. So light will be at 45 degrees in that diagram. I mean, okay, this is the frame of A, if you like. And in the frame of A, this is the way light travels.
Yes, sir.
45 degrees to the A's, the vertical and horizontal space.
Yes, sir. But so it will not be the same for B, right? As this will not be how B perceives it, right? Or
no, okay. So from B's frame, you have to, the diagram will look slightly different because then B's world line will be vertically upwards. A's world line will be slightly inclined. And so that will be the viewpoint from B. But the light ray will still travel at 45 degrees to the vertical.
Okay. Okay, sir. Okay.
Yeah, okay. I'm just bringing this online, I hope. Second. Okay, while I get my screen shared, you can continue to ask your question. 1 second. So from this event where A and B met, both of them were there at the same time, same place. Both of them send out light signals. Those two light signals go like this and like that. Is your confusion at that stage at all? Or are we willing to accept that at that instant of time, at that event, both of them are together? I mean, they are sort of standing next to each other.
Yeah.
And both of them shine their torch this way.
Yeah.
So those two torchlights will go hand in hand.
Okay.
And then they go and meet some event E2 somewhere in the future. And also some event they sent also in the opposite direction, go and meet some other event E1. And both E1 and E2 sort of reflect back the signals they receive. In the meantime, B has gone on its own merry way, continued to travel at its velocity. Yeah, I mean, the fact that B sent out a light signal while B was in motion relative to A is of no significance to the light signal.
Yes, sir. I think, yeah.
This is the essential and absolute point.
Yeah, now I got it, sir. Yeah.
Okay.
They sent it at the same point at the same time, and
Yes.
yeah.
Yes.
Okay, I think that clears it up, sir. Thank you.
Okay. Yeah. Yes. Okay. I invite you to reread it, think about it, draw it yourself. Yeah. Go ahead and. Okay. So then we start talking about the Lorentz transformations, and the thing here is that we have two frames, S and S prime, which are in uniform relative motion. So S prime is moving to the right relative to S. They are coincident. The two frames are the same when T and T prime are both 0. Okay, when at that instant, the two frames coincide. Subsequently, the S prime frame is moving to the right with some speed v along the x-axis of frame S in such a way that the y and z axes are unchanged. So it is purely rightward translation to make things simple. I mean, anyway, the translation is some direction. You choose that as the x direction. Okay, so now we proposed a formula for a Lorentz transformation, which we took to be the most general linear transformation between xyzt and x prime y prime z prime t prime, with the further stipulation that the orthogonal directions are purely some sort of spectators. They are not involved in this process. We gave some thought experiment why that is reasonable. Okay, one can think more about that. But for what follows here, I would like to work with this proposal, yeah, and see what the consequences are. So let me be more clear. X prime is a linear combination of x and t. So we write it as some ax plus bt, and t prime is some cx plus dt. We can leave y prime as y and z prime as z. That we argued last time. The main thing, let us compare with Galileo transformation. There x prime was x minus vt and t prime was t. So that was also a linear transformation. And the reason we wanted linear is to maintain Newton's first law. That is, if in the xyzt coordinate system, a free particle traverses a straight line at constant speed, that same general property must hold in the primed frame as well. So straight lines should map to straight lines. And that is ensured if you make a linear transformation. If you make a quadratic transformation or some other nonlinear transformation, straight lines can get warped and so on. Okay, so I invite you to take some example, write d prime as t squared or something, then you will see the problems that arise. Newton's first law basically will not apply to both observers, though they are inertial, both inertial. Okay. Now, of course, in Galileo's case, he had taken C to be 0. That is, time and space do not mix in this sense. That is, space does not come and affect the time change. Yeah, whereas relativity, special relativity is allowing that. It's allowing the new time to depend on the old space variable. This is the essentially new aspect, which was not present when we said t prime is equal to t. Now, there is nothing sacrosanct about t prime equal to t. One could have said t prime is equal to 2t also. It just means that the two clocks, one clock is running twice as fast as the other. We can handle such things. Or t prime is equal to t plus 23 or something. Yeah, that means the two clocks had different zeros of time. Such small changes we are allowed to make. They only complicate matters. It means that one person is measuring time in seconds, the other person is measuring time in milliseconds. That kind of difference we know how to handle. Or one person is having the 0 of time at the time of their birth, the other person is having 0 of time at their birth. So these times will differ by some constant amount. We know how to handle that and what that means. So we are not putting such quantities here. Okay, so now we made a further stipulation that D is positive, so that the sense of time past to future is the same for T and T prime. When T increases, T prime will also increase, holding X fixed. Yeah. So this was the further restriction we placed. If T prime was something like minus T, then the sense of times will be the opposite. So we are not thinking along those lines. I emphasize furthermore that the constants A, B, C, D can depend on the relative velocity of the frames. So A, B, C, D can depend on boost velocity V, or the speed, boost speed. Yeah, so we have said the direction is along X. So our aim is to find ABCD by some physical principles. So let us begin that. Okay, so what are those physical principles or comparisons we are going to make? We will now attempt to fix the constants ABCD, which, as I pointed out, could depend on the relative speed V by comparing the coordinates of certain distinguished events viewed from the two frames. So we will compare some distinguished events. I will mention what they are. Another constraint we will impose is that we will require that the speed of light is c in both frames. So both are absolutely basic requirements. I mean, the second one is coming from the second postulate of relativity. Let us see how to implement these general ideas. Okay. Okay, so first, let us recall that the origin of S at any time t has the coordinates x equal to 0, comma t. Okay. So the origin of S at various times will have these coordinates viewed by S. On the other hand, when viewed from S prime at some time t prime, the origin of S will have two new coordinates, because S prime is moving to the right with velocity v. X prime will say that the location of the origin of S is at minus vt prime at the time that S prime measured it. Okay. Notice I am not relating x prime to x. That relation is given by this linear transformation. We are not doing that. We are just saying that the origin of S, which is at x and t, when viewed from S prime, is at minus vt prime, comma t prime. Okay. Okay, so now we put this formula into the linear transformation. Okay, so I'm a little bit short of space here, but okay, I think I need to copy down that linear transformation here. So let me do that.
Sir?
Yes, please. Yes.
So when we talked about transformation from t to t dash,
Correct.
you said keep cx fixed and take d to be positive, right?
Yeah, I looked at a special case. I asked the question, do both of them have the same sense of time, in the sense that past to future, that sense do they agree upon? Now, mathematically, what we mean by that is when t increases, does t prime increase? To make that more precise, yeah, suppose x also is suddenly changing in the middle of that whole thing, then you cannot directly ask that question. So to make that question more precise, I said, suppose you keep x fixed, that is at a particular location in the original frame. Suppose t is increasing, will t prime also increase or decrease? That's the question we asked. We want to impose that it must increase. The way to achieve that is to make d positive.
So like I'm not able to physically interpret this. You're saying at a given position, like at a given point in S, the frame S,
Yes.
if time increases, what exactly do we mean by we want t dash to also increase? Like what do we mean by that physically?
Okay. Well, physically we mean we have two events. We have an event at T1 and T2 in the original frame. With T2 more than T1,
Yes, sir.
We want to view those two events from the primed frame. And what we wish to have is that those two events, somewhat colloquially, must also be in the same ordered manner. That is T1 prime and T2 prime. That is T2 prime should be more than T1 prime.
But we don't say anything about the interval, right? The interval can change, but like one thing precedes the other in both.
Exactly. What precedes what has to be maintained.
Okay.
It is okay that T2 prime minus T1 prime may be more than T1 minus T2, more than T2 minus T1. That's okay. We are imposing a less restrictive condition. We are just saying that the past to future should be the same for both. That's all.
Yes.
Okay. Okay. So let me copy down that transformation over here. X prime is equal to ax plus bt. T prime is equal to cx plus dt. Yeah, for obvious reason, I'm using capital letters because then capital C should not go and confuse with small c speed of light. Okay, so now we are going to put in the origin of the two frames, sorry, the origin of the S frame into this formula. So the origin of the S frame as viewed from S prime has location minus Vt prime. That must equal ax, a times 0, plus bt, b times t. And therefore, we get that b times t is equal to minus vt prime. That's how we got this formula. Similarly, I use this transformation and say that the time according to S prime must equal c times x, but that is c times 0, plus d times t. Okay, so I get the formula t prime is dt. Both of these refer to the origin of S, but they must both be true, and therefore combining these, I can I can eliminate, I can get now a relation between B and D because I can eliminate the T's. Yeah, B is equal to minus VD. Are you okay with that?
I am.
Okay, great. Yeah. So, I mean, T prime is just BT by V with a minus sign, but it's also equal to DT. So the two must agree. B is equal to minus VD. Okay. So remember, we had 4 constants, A, B, C, D. We want to slowly eliminate them and determine all of them in terms of the velocity V. So we have made one first step. We have eliminated D in favor of B. You can think of it that way. Okay, let us continue this game. Now let us view the origin of S prime. Previously we viewed the origin of S. Now I will view the origin of S prime. So the origin of S prime as viewed by S prime always has the coordinate x prime equal to 0 and whatever time you wish to view it at. T prime. On the other hand, as reckoned by S, what is that origin? Reckoned by S at their time t, the origin will be moving to the right, of course. So it will be at some location x equal to Vt at time t. So the origin of S prime viewed from S has coordinates x equal to Vt comma t. When viewed from S prime, it has coordinates x prime equal to 0 and t prime, whatever it is. Now we will put these two again into this transformation formula, Lorentz transformation formula. So let us do that. X prime is 0. So I say 0 is equal to AX. AX is AVT plus BT, which is BT. Yeah, so that's how I got this formula. AVT plus BT equal to 0. Then we go to the next one, which is to say that T prime is equal to CT plus, sorry, CX. I'm sorry, CX. I have to undo this. Cx, and for x I substitute Vt, Cx plus dt. Okay. Okay, so let us see how to proceed from this. From this formula, I hope, so it's worth following carefully. I can cancel the t's because this is true for any time t. Going to arrive at the result that B is equal to minus AV. But we already know that B is equal to minus VD. Conclusion, A must equal D. Yeah, that's all I want from here. All right. Any questions so far? It's nothing complicated, just a matter of substitution and elimination. So we have now determined two of the matrix entries. By the way, it's a linear transformation, right? So I can write it as a matrix. Perhaps I should have said that. X prime, T prime is equal to A, B, C, D, X, T. Yeah, so this is a linear transformation. Linear transformation can be represented by a matrix. So the formula we wrote previously is the same as this. So far, what we have shown is that this off-diagonal entry, the northeast entry, is minus V times D, and the matrix diagonal entries are equal. A has to be equal to T. We have just established that. Any questions so far? Okay. Now, okay. Yes.
We've taken that at time is equal to 0.
Yeah.
The origins of both coincide for some reason.
Definitely. Yes. We have made that assumption for simplicity. It could have been that they didn't coincide, and you are welcome to work with that. That the two frames differ by a translation at t equal to 0. That is entirely possible.
Any information, right?
No, we are not losing information. See, we have to ask what question we are trying to answer now. We are addressing specifically the question of how to relate the coordinates in two frames that are in relative uniform motion. That's the question we want to answer. The thing you are raising is how do coordinates relate if two frames are simply translated with respect to each other, just some fixed translation. We know how to write that, because that has nothing much to do with relativity. That will just say that, I mean, okay, are their times the same or not? You have to tell me, or we have to decide. But if you are saying the two are just translated, then we will say that R prime is equal to R plus A. Yeah. So then X prime will be X prime plus X naught. Sorry, X prime will equal to X plus X naught. Y prime is equal to Y plus Y naught. And Z prime is equal to Z plus Z naught. Yeah. And this is an absolutely fine transformation, and you can decide maybe T prime is equal to T plus T naught. Yes. This would correspond to a space-time translation. That is exactly the kind of thing where you center your coordinate system around your town, and I center my coordinate system around my town. You center your time around your time of birth. I do it around my time of birth. And we do know that the laws of physics, we believe, are invariant under space-time translations. And therefore, these transformations which I have written down must be a symmetry of the laws of physics. Yeah. So that homogeneity of space and time are to be implemented. Right now, we are asking a slightly different question. How do things transform if you make a velocity boost? So to avoid these things, I'm separating out this issue.
So actually, I was thinking maybe this translation vector might depend on the velocity, but maybe that's not possible.
No, they are both in our control. No, they don't depend. I mean, you can translate a frame relative to another frame, a fixed translation. That's it. It's not a time-dependent translation. A time-dependent translation is more like a boost. Yeah. So yeah. So that's what we are now addressing. And we are not addressing questions about non-uniform translations and so on. Yeah, where this x naught itself depends on time, then no, this is no longer inertial. I mean, if you're changing your frame in a non-uniform way, then that's not an inertial system anymore. Except if it is uniform motion. Okay, so that was rho myth. All right, any other questions? All right, so story so far, we have determined by comparing the coordinates of the origins of the two frames that A is equal to D and B is equal to minus AV. Right. Now let us go on to impose the next condition, which is that the speed of light should be the same for both observers. Yeah. So let us look at a couple of different scenarios. Let us suppose that a light pulse is emitted from the origin, common origin, t and t prime both equal to 0, common origin, and it is observed later along the x and x prime axes. So the light pulse travels towards the right, and it's observed along the x and x prime axes. By the constancy of the speed of light in this frame S, the place where it is observed at the time t will be x equal to ct, because it's traveling at speed c. Okay, so we are looking at the event of observation of that light pulse by the frame S, observer S, at time t, it will be at the location ct. Now, what about that event as viewed from S prime? That same event would have some coordinates. Well, it started at the same place in both frames, travels at the same speed, so its location should be ct prime if S prime is observing it at time t prime. The temptation we have to avoid is to think that t prime is the same as t. There is no such concept. Okay, our aim is to find what t prime is in terms of t. So we just say that same event, suppose it has the coordinate t prime as viewed by S prime, then at the time t prime as viewed by S prime, that light pulse will be at the location ct prime, because we know its speed is c. Okay, so now we have got the coordinates of the same event as viewed by two observers. So have coords of the same light observation event viewed by two observers. So now we want to put them into the general formula, linear transformation, to see what relations this imposes. So let's do that. So the recall that we had said that x prime is equal to ax plus bt, right? So I'm going to substitute for x prime as ct prime. That's what we just said. Ct prime must be ax, but x is ct plus bt. So there we are. Ct prime is act plus bt. Next, I go to t prime, which was cx plus dt, generally speaking. Therefore, t prime is equal to c, for x I substitute ct, small ct, plus dt, that is simply dt. So we get the second formula, t prime is equal to capital C small ct plus dt. Okay, so now we need to see what we can do with these two formulae. Well, we can use what we had learned earlier already, that the diagonal entries of the matrix are equal. So A equal to D. Yeah. So we have to combine these two. Let us do that. Okay. I can combine these. Okay. So what do I have? I will equate these two, right? I will equate CT on both sides, CT prime. So I'll get ACT plus BT on the one hand is equal to C squared T plus dct. Yeah, I'm writing ct prime. I've written the second equation for ct prime and equated it with the first equation for ct prime. And now I will further use the condition that A is D. Okay, so far? Any question?
Sir, I just wanted to clarify that we can do this because it's the same event, so we can convert the coordinates from one system to another. And since we started from the same point and light is traveling at the constant speed c, both these coordinates, once we convert it to the same from one coordinate system to another, both of them have to be equal since it's the same event.
Yeah. Okay. You have said several things. They are not all related. So let me disentangle a little bit. You have a common event. You have an event like your birth. Okay. That's an event. Two observers can view them. They can assign coordinates to this event. Primed coordinates, unprimed coordinates. The speed of light is not involved in this process. Lorentz transformation simply relates the coordinates of any event between frames. So I can put in the x prime coordinates, t prime coordinates, and the xt coordinates, relate them through this linear transformation. That will give you a relation between the two. Yeah. Separate matter is how did I get x prime and how did I get x? For that, I use the constancy of speed of light. In order to write this formula in the first place, I use that the speed of light is c as viewed by s, and as viewed by s prime, also the speed of light is c.
Okay. So Lawrence, we had that relation anyways.
Yeah.
We're just using the speed of light to create the event or to specify the event that we're
correct. Exactly. We are using light to create some interesting events. Exactly.
Okay.
Yeah. And this is where see, so far when I wrote that this linear transformation, nowhere here has the constancy of speed of light entered. Okay. This is just some arbitrary linear transformation. Only now we are bringing in some event that depends on light and so on. Okay. All right. So any questions so far? I have arrived at this formula by viewing this distinguished event from both frames and relating them through that linear transformation. If you're okay with this, we can now go ahead with this little algebra. A is already equal to D, so that's where I made this substitution. So ACT here and ACT here get cancelled, and the equation then tells you that B is equal to CC squared. Yeah. And that's what I've written here. B upon capital C is square of speed of light. All right. Now let us combine that with our earlier result that B is minus AV. Okay, so let me recall that B is equal to minus AV. So suppose we combine these. Now we have got three relations. A is equal to D, B upon C is something, and B is related to A in this manner. And therefore, I can, putting that here, we get that C is equal to B upon C squared, which is minus VA upon C squared. Yeah, so capital C is minus V upon C squared times A. It's nothing complicated here, it's just some algebra. Okay, so basically we have taken care of D in terms of A, it's equal to A. We have expressed B in terms of A, so B is also taken care of. C is also taken care of. C has been expressed as a function of A. Great. So A is the only unknown. And what do we want to express A in terms of? Please tell me.
V function of velocity.
Exactly. Yeah. So far, what is the message so far? So far, expressed B, D, and capital C in terms of A. So the remaining aim is to find A in terms of v, okay, which is the boost speed. Of course, everything will depend on speed of light also. So the speed of light will also enter. Right. So the remaining aim is to find A in terms of V and C. That is the last event we are going to compare. So far we looked at light pulse traveling along the X direction. So let us now look at a light pulse emitted in the Y direction. Okay. So let us, any questions so far? Okay. So let's look at a light pulse emitted from the common origin at t prime 0. Let us suppose it is observed later on along the y-axis in X, okay, along the y-axis in S. So it was emitted from here. The S prime frame is moving rightwards. The light pulse later on is observed on the y-axis of S. So let us suppose that is observed on the y-axis of S. So as far as S is concerned, the X coordinate of that event will be 0, yeah, on the y-axis. The Y coordinate, given that the speed of light is c, must be ct, and the time at which it happens is whatever time, we just call it t. Okay, so we have now identified a distinguished event. Now we want to view this event from S prime. Let's do that. Now S prime has moved to the right in the mean time, has moved to the right. So as far as S prime is concerned, what are the coordinates of this event? Yeah, that is somewhere here. So in S prime, the horizontal coordinate x prime is equal to minus vt prime. Yeah, because it is back here. The S prime frame has moved a distance vt prime during the time that has elapsed. So it is equal to minus vt prime. And what is the vertical height of that event as far as S prime is concerned? Well, for that we use this little triangle. This little triangle. Okay, so yeah, y prime. Okay, so I have written the formula over here. So I hope you will help me with this. So y prime squared plus x prime squared has to be equal to this hypotenuse squared. That's all we are writing. So y prime squared plus x prime squared is equal to hypotenuse squared, but that hypotenuse is the distance that the light pulse is at from the origin of the frame. But light travels at speed c according to all observers. Therefore, the light must have traveled a distance ct prime. And now once you are looking at square of hypotenuse, I put a square there. Please see whether you follow this. This is the crucial last step. I'm just using this triangle. The light pulse has traveled from the origin of the frame S prime to this position. Distance covered must be ct prime. Yeah. Therefore, we get y prime squared plus x prime squared is equal to ct prime whole squared. Okay, so then we can take the x prime squared to this side and take a square root and write y prime as square root of ct prime whole squared minus vt prime squared also, because y prime was minus vt prime. Yeah, and as far as S prime is concerned, this event has some time t prime. Okay. Yes, please. Shubham, yes.
I didn't get this prime coordinate. Can you explain it once again?
Yes, let me go slowly. Speed of light is c. Yeah, so in a time t prime, so okay, the light pulse has moved upwards according to S, vertically upwards according to S, and S is observing it at some location y equal to ct. We want to know what are the coordinates of that event as reckoned by S prime. Now S prime, in the meantime, the origin has moved up to this location towards O prime. So the the light pulse has reached this location. The distance covered,
Okay, sir.
the distance covered has to be Ct prime, because T prime is the time according to S prime. The distance covered has to be Ct prime, because in that time, that is how far light travels. And then I am simply using Pythagoras' theorem. Is that okay?
Yes, I mean in O prime's frame, the light even in O prime's frame, the light will be traveling right? And this
Okay.
dt is what I don't get that.
Okay. Let us say that in the O frame and the S frame, you have a torch like this, vertically held torch, and it emits a signal upwards when the two frames coincided. So that the light signal will simply go upwards as far as S is concerned. Then that light pulse will go and, yeah, that light pulse goes and hits some detector later on at some time t according to S. That is the event we are interested in. Now we are viewing that event from S prime. There is a separate question. Suppose you have a spherical wavefront of light. How will S view it? How will S prime view it? That's a very relevant question. I will come to it shortly. Okay, maybe your question is partly concerned with that. Yeah, I mean, okay, I'm just speculating, but that is also an interesting question, which I think deserves attention. I will talk about it. Okay. Any question right now about how I know my paper is full of symbols. Please excuse me. But the key formula we have just derived now is y prime is equal to square root of ct prime whole squared minus vt prime whole squared. Okay, so those are the coordinates of this event. So let us now compare those coordinates using the linear transformation, which is always valid. Let's try then. What does the linear transformation say? It says that t prime is equal to cx plus dt, right? That is one of the things it says. Let's apply that. Say t prime is equal to cx. What should I substitute for x?
Zero, sir.
Excellent. So I have to put 0 because my event as viewed by S happens along the y-axis. Therefore, x is 0. So great. So I have to throw this away. Yeah. And just write dt. T prime is dt as far as this event is concerned. So that is the first formula. Okay. Then I go to the next formula, which says that x prime, do I need it even? Yeah, okay, x prime. Oh, no, yeah. My next formula simply says that y prime is y. This is also part of the linear transformation, right? Y prime is y. So let us exploit that. Y prime is, I hope this is the one I want. Let us see. Y prime is the square root business. Yeah, y prime is that square root. I copied it here. Y is ct. So equate them. Simple as it is. So the principle is very simple. Equate y and y prime. Now we just have to simplify these expressions. So I hope you will help me do that. Yeah, so let me do that by the side or something. Yeah, suppose I use this t prime is dt and put it over here. What will it give me? It will give me c squared. I will square this whole expression. C squared t squared is equal to c squared d squared t squared. I'm substituting t prime as dt minus v squared d squared t squared. Yeah, something very nice is going to emerge from this. Nice. Any question about how I reached here?
No, sir.
Okay, very good. I do encourage you to pay close attention. The t squares cancel, and we get a remarkable formula for d squared. Now it's an absolute formula. We're not doing this business about relating a to d and b to c and so on. It's now an absolute formula for d squared. It says that d squared is equal to c squared upon c squared minus v squared. Yeah. Or taking the square root, positive square root, because remember, this is orthochronous. We want the sense of time for both observers to be the same, past to future, and therefore I take the positive square root and divide by c throughout. So this is 1 upon 1 minus v squared upon c squared. Taking a square root, I get this formula for d. In other words, d is equal to 1 upon square root of 1 minus v squared upon c squared. Okay. Now our job is done, because we are going to call this quantity gamma because it appears many times. So it's convenient to introduce the simple gamma for the factor 1 upon square root of 1 minus v squared by c squared, since it appears frequently. This factor is what ensures you could, as a loose interpretation, it ensures that the speed of light is the same in both frames, because it is by imposing that condition that we got it in the first place. Yeah, I make a further observation that, okay, we have assumed that v is less than c. Now d is, of course, gamma is of course positive, but not only positive, it is always more than 1. Yeah, because in the numerator, I'm taking something away from 1. 1 minus a positive quantity. So the denominator is always less than 1. Therefore, the quotient is always more than 1. So gamma is always more than 1. Furthermore, we observe that as the boost velocity or speed approaches c, you make larger and larger boosts. Then the denominator goes to 0 when v approaches c, and gamma goes to infinity. Okay, so just a couple of properties we are observing right now for future reference, that as the boost goes to velocity goes to c, gamma goes to infinity. So gamma is bounded between 1 and infinity. That's the physical region. Yeah.
So we are assuming that v can't be greater than c.
Yeah, in fact, we have already assumed that in this formula that I wrote, this Pythagoras formula, that already assumes that v is less than c. Otherwise, this quantity within the square root will be negative. So you are absolutely right. In this analysis, we are making the assumption that v is less than c. That is, the boost is at most at speed c, but not more than that. And we are building a framework to relate frames that are in motion relative to each other uniformly, at most with speed c. You can ask what happens if one frame goes at a speed more than c. It's an interesting question. We are not addressing it right now.
Sir, what would be the physical significance of gamma going to infinity?
We will see. Gamma going to infinity will have physical significance. It will, so just to preempt certain things, anyway, our course is ending, we don't have that much time. So gamma going to infinity, okay, just to put it very colloquially, see, gamma here is relating to frames, but I'm now going to talk about a particle. Suppose gamma has to do with the velocity of a particle, then increasing the value of the speed of the particle will make gamma go to infinity. Physically, it will mean that you will have to supply an infinite amount of energy to make that particle go to a speed which is approaching that of light. Okay, so yeah, so I'm saying it in a very rough way, but it is basically correct. If you want to accelerate a particle to a speed approaching that of light, like an electron, It's possible to get it closer and closer to the speed of light, but because gamma goes to infinity in that process, consequently also the momentum that you'll have to transfer to that particle will also become unbounded, and the energy you'll have to supply will also be unbounded. So those are certain implications that come from this. Yes.
Is there a physical significance of gamma in general, not like it going to infinity, but like in general?
I mean, gamma is simply some symbol for some thing depending on the velocity of the boost. That is all. There is nothing deep about gamma. No, the gamma is, it just appears here and there, so we call it by some name. Yeah, but it is a very useful quantity. You will see its expression appearing in the relativistic momentum for a particle, relativistic mass, energy, and so on. So it's just a convenient symbol. I would not say that gamma has some deep physical significance. Momentum has a deep physical significance, so does energy and other such things. Gamma is simply some parameter that quantifies the boost that you are concerned with. Yeah, okay, so that was Siddhant. All right, so here we are. Let us now summarize our achievements, all this laborious process in the last half an hour or more. A was equal to D. Remember, the diagonal entries of the matrix were equal, and therefore both are equal to gamma. And then we also had concluded that B is minus VD, and therefore B is equal to minus V gamma. So I'm just summarizing the results. And finally, C was equal to minus V upon C squared times A. So I had written that somewhere in this mess. Here it is. C is equal to minus V upon C squared times A. Yeah. So anyway, let's now focus on the summary here. Capital C is minus V upon C squared capital A. Now substituting for capital A as gamma, it becomes minus gamma V upon C squared. Okay. So we have achieved something quite significant. We have expressed all the constituents A, B, C, D purely in terms of the physical boost speed and, of course, the speed of light. So now we can summarize the Lorentz transformation from frame S to S prime. So we may summarize the Lorentz transformation from S to S prime, moving at velocity v along x. What is the formula then? X prime is equal to ax plus bt. So simply substitute. Ax becomes gamma x and bt becomes minus v gamma. Yeah. So, but I would like to take the gamma as a common factor and write x prime as gamma times x minus vt. Okay. We are going to interpret this in some limiting cases shortly, so you will understand it better soon. Y prime was just y, z prime was just z. Okay, so those are unchanged. Finally, we had that t prime is equal to capital Cx capital dt. Yeah. So for capital dt, d is gamma, so I get gamma t here. And for Cx, I substitute for C as minus gamma V upon C squared, minus V gamma upon C squared. So that is T prime. So let me read it once again. X prime is equal to gamma times X minus Vt. Okay. If you remember, our Galilean transformation said that gamma was X minus Vt. X prime was X minus Vt. Galilean transformation. So the effect of special relativity has been to bring this gamma in. That is the only effect as far as the x to x prime transformation is concerned. The orthogonal directions are simply spectators. And finally, the t prime coordinate is given by gamma times t minus vx upon c squared. Okay, so I encourage you to go through this derivation yourself slowly and try to obtain it yourself. Well, it's worth checking dimensions also. What's the dimension of gamma, by the way?
Sir, I think it's dimensionless.
Very good. Yes, Gautam is right. And so is, I forget who else spoke. I didn't notice. Yeah, so gamma is dimensionless. So I can say length to the power of 0. after all, it depends. So gamma was 1 upon square root of 1 minus v squared upon c squared. V and c are both the same dimension of speed. So this quantity is dimensionless. So gamma is dimensionless. So that's okay. T prime and t will both be measured in seconds, for instance. Now this Vx upon c squared again has dimensions of time, because V by c is dimensionless. Then your remaining factor is x by c. Length upon speed has dimensions of time. So at least dimensionally, these formulae are consistent. So I would encourage you to, I mean, these transformations are encountered frequently in relativity. So I hope they will become part of your memory. Yeah, they're useful. Now the inverse transformation from S prime to S is obtained. You can do it in two ways. Just view it as the inversion of a matrix. Yeah, X is equal to ABCD X prime. You just take the inverse of the matrix, you'll get it. But physically, we can think of it in a simpler way. The inverse transformation is simply obtained by reversing the sign of the relative speed v. Yeah, so if I reverse the sign of v, I will get the transformation automatically. The two frames will be reciprocally related. Yeah. In other words, to say it clearly in English, if I reverse the sign of v, I can then say that S prime, or let me say that S moves with speed minus v relative to S. Okay? I mean, this statement is the same as the statement that S prime moves at velocity v relative to S. Yeah, I'm restating the same thing. Yeah, and therefore, since S moves with speed minus v relative to S, I can get the transformation from X in terms of X prime by replacing v by minus v in the previous formula. I hope I didn't confuse you in that statement. Please stop me if there's something I can clarify here.
Sir, I just wanted to ask, would this be the same as, like, right now we've taken let the main frame to be S and then S prime, right?
Yes.
Would this be like changing v to minus v? Would this be the same as taking S prime as the main frame and then taking S as the
as a new frame? Correct, correct. Yeah, that's exactly what we are doing. We are now viewing S prime as the main frame, as you call it, and then the frame S is moving leftwards with velocity minus v, or leftwards with speed v. Yeah. So then you can use the very same formula we just derived, but since the boost is now minus v, you just replace all x primes by x's, all x's with x primes, replace minus v's with plus v's, and you will get the transformation between the two.
Okay.
Yeah, so that's exactly what we have done. We have replaced our notion of main frame and subordinate frame. Okay.
We did never, like in a derivation for this, we never accounted for these, I mean, for the fact that the inverse transformation should work out as it were.
Oh,
like
yeah.
in this case, when we calculated it works out, as in the gamma works out, but like
when you say the gamma works out, I'm sorry, I didn't understand what
I mean,
you
like when we actually put x as x dash, like for the same event, and then we transform forwards and back, then sort of it multiplies out. And like the gamma goes from the denominator to the numerator. Like because like basically when you try to when you have x dash as x, and then you again try to do the opposite transformation for the same event with the same coordinates. So like at this moment, the gamma goes to the denominator, right?
Oh, okay. Wait. No, I think there are several different things.
That's slightly,
yeah.
I mean, sorry, that's my,
okay. Now let me try to think what you are trying to convey. See, we have already found that if S prime moves at Vx hat relative to S, then X prime Y prime, X prime T prime is equal to some A, B, C, D, X, T. Okay. And we have determined what A, B, C, D are explicitly in terms of the speed V. Now we want to, somebody comes up and says, no, my setup is different. My setup is if S moves at minus V X hat prime relative to S prime, then what is X T expressed in terms of X prime T prime? We are trying to answer the second question.
Yes, sir.
Answer to that second question is simple way to get the answer. Take this matrix and just replace all occurrences of V with minus V. End of story. Physical justification is that you just read this expression and read the next expression. They are practically identical. It is just my convention to call this S prime and that call that S. You use some other convention, call this S and call that S prime. My velocity has V here is minus V here. So everything else should not be affected. I should be able to use the very same formula with primes interchanged and V interchanged with minus V. So I will get something here, and that should be the linear transformation. Yeah, if you would like to check it, I invite you to take this matrix, and this is a good exercise. Take this matrix that we have defined here, ABCD, that is gamma, gamma, and so on. Compute its inverse and see whether that agrees with the formula written here. Maybe you will feel more confident once that is done, and that should be done.
Yes, sir.
Okay. So Romit, can I clarify anything further in this?
I think so. I mean, the question I was trying to ask was like, sort of the fact that this, the fact that the inverses come out to each other, like it sort of falls out from the formula, right? So we haven't checked for that, like when we're defining the formula.
Okay.
So the fact that V and V minus V, like
define inverse matrices.
No, we're not defining inverse matrices. But just the fact that the transformation one way and then back.
Yeah.
It maps back to the same point.
Like
we haven't checked for that, so that works. So would that always work? That's what I'm saying.
Okay, that is a consistency check. Okay, what you are trying to get at, I think partly, or let me interpret it as saying, if you make a boost by velocity V and then a boost by velocity minus V, the resulting transformation should be the identity. Now that should be a consistency check, and the question is whether it is true or not. Yeah, so in other words, you can take the ABCD matrix. So let me call that matrix lambda as some A of V, B of V, C of V, D of V. Yeah, and then so this is lambda of V, and then I can define a lambda of minus V simply by substituting minus V's wherever there was a V. Now I claim that if you multiply these two matrices in whatever order you wish, you will get the identity. Lambda of V, lambda of minus V is equal to identity is equal to lambda of minus V, lambda of V. Okay. So this is yet another statement. I hope it will have some value for you. But you are on to something. You're on to discovering that Lorentz transformations form a group. Okay, so I can only say good. Okay, but please tell me if I can help further right here now.
Thank you. That's a bit of a detour.
Okay, fine.
Sir, could you just scroll up a little so that we can see the values of ABC?
Yeah, okay, I can write the matrix if you like. Gamma, gamma, B is minus V gamma, C is minus V gamma over C squared. This is our funny matrix. Gamma is a common factor in all matrix elements. Okay, so Siddhant is going to check my statement. Now, okay, I hope my dimensions and all are not wrong or something. So, and not only Siddhant, the remaining 55 also should check this.
No, so I was just going to like do the matrix inverse multiplication. Like
exactly, yeah, yes, that is a worthy calculation, which is strongly encouraged. Though maybe in your spare time after the class ends, because we have only 10 minutes left. Yeah, but okay, any other questions that others would like to ask now? Okay, I needed to make a couple of physical interpretation. Let me complete that. Oh, so where was that written? Here it is. Now, what happens in the so-called non-relativistic limit? The non-relativistic limit, first of all, is a limit where V upon C goes to 0. Okay, so colloquially, some people will say it is the limit where the speed of light tends to infinity. Okay, I mean, it's okay to say that, except that I would prefer to say it's the limit where the speeds of the relative speed upon the speed of light goes to 0, because this is a dimensionless quantity. Right? In physics, we always like to compare dimensionless quantities to dimensionless quantities. 0 is a dimensionless quantity. Yeah. So dimension full quantity, when we say it is large, typically in physics, you will ask large compared to what? So your answer to that question is large compared to the velocity of the boost. So that's why this is a nicer way of saying it. But both are okay. Yeah, okay, I should not have been so cavalier. I should not have said that 0 is dimensionless. 0 is dimensionless, but a mass of 0 kilograms is also dimension full. So one has to read the statement carefully. Yeah, okay, so let me, so okay, I have not finished the sentence. In the non-relativistic limit, where V upon C goes to 0, what happens to gamma? Let us see. Well, in this limit, what should we expect physically speaking? We should expect that the Lorentz transformation, whatever it may be, should reduce to a Galilean transformation. That is a Galilean boost. Yeah. In fact, well, what happens in this limit? Let us see what happens to gamma. Gamma, remember, was 1 upon square root of 1 minus V squared upon C squared. So when V upon C goes to 0, non-relativistic limit, we will get that gamma tends to 1. So the gamma factors go away, and x prime, which was gamma times x minus Vt, just becomes x prime is equal to x minus Vt. And gamma goes away elsewhere as well. The second term here, the V upon C squared term, can be ignored. And therefore, T prime just becomes T. Okay. The V upon C term goes to 0. So the second term here is ignored, and gamma became 1, so T prime is T. So in other words, the non-relativistic limit, we do recover the Galilean transformation. So which principle have we checked? Please remind me.
So this was correspondence.
Exactly, yeah. So this was the correspondence principle that Einstein was guided by, that whatever newfangled theory you make in the non-relativistic limit should agree with the theory of Galileo and Newton. All right. Okay, so I believe that Siddhant has checked that the matrix multiplication cancels out to give the identity transformation. Okay, thank you very much. So others also may feel encouraged by that. And Romit, who raised the question in the first place, that if you make a boost by V and then a boost by minus V, the composition should be the identity, no boost at all. and you can check it in either order. Yeah, I mean, whether you first boost by minus V and then by V or the other order, that doesn't matter. You'll still get the identity. Okay, so let me now just complete this short discussion. Well, okay, there is a more general formula. If the velocity is not along the x direction, you can ask what is the formula. I'm not deriving it over here. Yeah, but let me just state it here. So more generally, if S prime coincides with S at time 0 and time prime 0, but moves at the constant velocity v relative to S, now v could be in some oblique direction, then the coordinates of an event x prime comma t prime, where x prime really is boldface, so that means x prime, y prime, z prime, t prime, with respect to S prime are related to those in S by the Lorentz transformation that is given here. It is very similar to what we wrote before. X prime, boldface x prime vector is gamma times x minus vt, where v is again the velocity vector. Yeah. And t prime is gamma times t minus, previously it was x times v, now it becomes x dot v. It's only the component in the direction of the boost that contributes. Orthogonal directions do not contribute. Okay, so this is encoded in this formula. I just want to note it here for reference, and with the observation that spatial coordinates perpendicular to the boost velocity v are unaffected. They are unaffected, and also they don't affect the other ones. So the I mean, if v is in the y direction, then z prime will equal z. The gamma will not appear in that part of that formula. Okay, so okay, but let me let's this is not something I want to dwell upon right now. I will let's come to that later on. Let me in fact I should even write it properly in the first place. So yeah, so I should even rewrite this. So please hold off on that formula for now. We don't even need it for right now. Okay, but one thing I do want to finish with, but this is a bit of a small exercise for you. I will do a small version of it in a moment. Yeah, or okay, let me go to a little bit of physics. Yeah, that would be a nice place to end this lecture with. So let us interpret the null result of Michelson and Morley using this Lorentz transformation. Okay, so this goes back to what Shubham was also asking, I think perhaps. Suppose S and S prime are as above, and at t and t, so they both coincide at t and t prime equal to 0, the frames coincide. Yeah. Now, suppose a light pulse is emitted from the origin, common origin, x, y, z all 0, x prime, y prime, z prime all 0, t and t prime both 0. Okay. So at that event, a light pulse is emitted and spread spherically outwards. Now at time t, the wavefront in the S system is on the spherical surface x squared plus y squared plus z squared equal to c squared t squared. Okay, so we are viewing it from the S frame, pulse of light spreading in all directions, speed of light is same in all directions, so the wavefront must be a sphere of expanding radius given by ct. Now let us view this from the S prime frame. What does the wavefront look like? That is the question we wish to address. Okay, now using the Lorentz transformation, there's a little calculation here to be done, which I can do, but maybe out of time. So using the Lorentz transformation and the formula for gamma, or what you need here is the square of the gamma. For a square of gamma, it can be shown that this identity holds. Y prime is y and z prime is z, so they don't play too much of a role here, but one can show that this squared difference, x squared minus c squared t squared, is equal to x prime squared minus c prime t prime squared, c squared t prime squared, I'm sorry. This identity can be shown to hold from the Lorentz transformation. So this, I strongly encourage all of you to check this thing, but I'm going to use it and tell what the implication is. What it means is that x prime squared plus y prime squared plus z prime squared minus c squared t prime squared must be equal to x squared plus y squared plus z squared minus c squared t squared. Okay, because the y prime squared was equal to y squared, z prime squared was equal to z squared, so I can add them on without any effect. Yeah, and it is then saying that if this is equal to 0, for instance, then this one will also be equal to 0. Now, what is the physical interpretation? This being 0 is the statement that the wavefront lies on a spherical surface of radius ct in the S frame. This being 0 is the analogous physical statement that the wavefront, the same wavefront, when viewed from the primed frame, again looks like a sphere with the radius ct prime. Okay. So the speed of light is the same for both. The wavefronts look the same. What shall we say? Thus, both observers see a spherical wavefront that expands at the same speed c, and lo and behold, absolutely remarkably, there is no trace of the relative velocity v. Okay. S prime frame, though it's moving relative to S, sees a perfectly spherical wavefront going outwards without any trace of the velocity of the old frame S. Yeah. Light doesn't care about that there is another frame that was moving in a different way. Light doesn't care about that. Yeah. So the Michelson-Morley experiment was designed to measure a difference in the speed of light in directions parallel to and perpendicular to the Earth's motion. Okay, so that was the way it was set up. Just trying to find a difference between the speed of light. So there is presumably some kind of ether there, and looking at different ways in which the Earth was moving through the ether. Yeah, and along the Earth's motion relative to the ether and maybe perpendicular to the Earth's motion. So then the relative velocity between Earth and ether would be different in those two situations. And so Michelson and Morley thought there would be a difference in the speeds of light in those two directions. That no such difference was measured is consistent with the constancy of the speed of light for all observers. And this feature is already now encoded in the formula for the Lorentz transformation. That both observers, though they are moving at some relative speed v, both see this a spherically expanding wavefront, irrespective of the speed of the other frame. Yeah, so this is the conclusion that I would like to stop here with. There are some more questions, I think, from others. Pratim Ghosh has also sent a question. Let me try to address those next time, along with this calculation, which I think is also worth doing. So we will do that next time. Any questions right now? So we have covered some ground. These are subtle concepts. I encourage you to please go over it in your spare time. If there are no other questions, I will leave you with the assignment 8, which is due this weekend, end of this weekend. Please do submit it in time. Okay, if no other questions, we shall halt here and meet next Tuesday. The exam schedule has been announced. So the Classic Mechanics 1 exam is scheduled for Tuesday, December 28th morning. So further details about that we will see. Okay, so have a good afternoon and a good lunch.
Thank you, sir.
Thank you.
Thank you, sir.
Yeah.
Thank you, sir.
Yes, you're welcome.
Yes, sir.
Sir, I just wanted to let you know I sent you a mail about.
Yes, I did receive your email, so I will look into that and see what I can do. I have received. Yes, sure. Yes, Siddharth.
Yes.
Thank you, sir.
All right, you're most welcome.